Good afternoon, everyone, and I want to thank for this opportunity to talk about ESD or electrostatic discharge. Many people in the beginning didn't know what ESD stood for. Some people thought it was evil spirited devices because people didn't understand why when you touch a device, why should it get damaged? And many managers in companies wouldn't believe that there is something called electrostatic discharge that can harm IC devices. I belong to the ESD Association. This is a worldwide organization now bringing a lot of awareness about ESD because it is, as you will see, it's a major threat to most of the electronic devices, especially now with so many consumer applications for laptops and cell phones, and all of these are subject to a lot of ESD events. Now somebody is taking care of this, otherwise none of these electronics would even be working. So what I want to do is give you a basic understanding, and then I will talk about some of the physics and some of the design of protection circuits to protect the IC pins from this external threat of ESD. So let me begin by with this introduction. Also, I welcome you to ask questions at any time. I try to make this more fundamental in nature, and I would think the whole thing began with the Big Bang. And so there was the universe, that the Big Bang that happened and the explosions that took place. So what we think is probably that's when ESD has happened, the first pulse. Okay, so that is what it's all about. Now, what happened? Everything was going dynamically throughout the universe, but nothing is of concern to us because our planet only came much later. And then 50 million years ago, what has happened? What's the major event that has, about 50 million years ago, was the comet that struck the Earth. There were dust particles everywhere. And who was around at that time? The dinosaurs. So what I think is they all became extinct from this lightning, which is actually a form of ESD. If they had only known how to build lightning rods, maybe they would have survived. So the next major threat came on the electronic devices. Till the late 60s, nobody paid any attention to ESD. Most of the electronics that were built had a built-in ruggedness to them. But then devices started becoming sensitive. Now there is the Michelangelo's painting of the ESD pulse that might have permanently damaged the human brain. And that is the IC chip now that is a big threat of ESD. So that's what we're going to talk about. Why is this such a major threat? What can we do about it? And if we don't do anything, what else could happen into the future? So let me just begin by telling you, ESD is what is around us each day. There is ESD charge, electrostatic discharge, that happens every day. And you're all familiar with, in the winter time, walking around and touching a doorknob, and you see that static discharge. It is pervasive and can damage IC during handling, assembly, shipping, and testing. That's what we want to understand. And it can cause destruction of electronic devices in automotive, medical, and consumer applications. Now, it's pretty dangerous if you have ESD failures in an automotive environment. Is because a lot of the electronics now are into the automobiles, and you don't want anything to fail. That is the major reason for concern. And of course, the same thing with the medical devices. So this is the reason that many people are worried about how to control. So ESD can be controlled. If you don't control it, that is just going to be tens and thousands of volts everywhere, discharges, and you can't do anything about it. In fact, you can't build any electronic devices if you don't know how to control it. So ESD can be controlled, and you also, even if you control, you can make it go away. It will be some minimum level you can control to, and based on that level you can control to, you have to build protection circuits at the IC chips to absorb this external ESD thread. That is, simply you place some kind of diodes at the IC pins so that they can clamp the voltage and protect the IC pins. Now, besides ESD, there is also something called electrical overstress. This results from the exceeding the specs for voltage and current can also cause severe damage. So ESD is something that happens, but EOS is something that is a cause of carelessness or mishandling of not following the specs. If I sell you an IC and I say the power supply should be 5 volts, you shouldn't be applying 7 or 8 volts on that power supply. And you damage it, that is an electrical overstress. So there is a distinction between ESD and EOS. They are both related and not related at the same time. So what we need to understand is, where do we go from ESD into EOS regime? So what we will do is, first, we'll examine the nature of ESD, the physics of ESD, and the methods to design protection for the IC chips. So semiconductor manufacturing, you have a lot of typical failures that can happen while manufacturing in the production areas. You have mobile ions, there are a lot of mysterious causes, assembly, unknown during the fabrication, and then you have ESD or EOS. So you can see this is the Pareto analysis of the percentages of failures that can occur. Notice something, ESD, EOS stand out around 35%. What is amazing is that the last 30, 40 years, that number remained constant. Then you would be wondering, then are you doing anything about it? Yes, we are doing everything about it. But at the same time, you get more and more advanced technologies, more and more sensitive devices, more and more applications, more and more people involved in careless use of devices, all of these contributing to constantly remain at that thing. And this is the ESD, EOS is a major cause for the semiconductor failure. That is the reason so much of this has been now trying to understand. Now, out of the ESD, EOS, actually 97% of the failures are from electrical overstress. So only 3% are from ESD. The reason is we are doing something about ESD. Nobody is doing anything about EOS, which is now completely dependent on customer applications, and there are lots of work going on now to reduce that as well. If you don't control and protect against ESD, it won't remain at 3%. It would be a lot higher. In fact, sometimes the yield could be just zero out of a wafer manufacturing. So that is the reason. Now, this will continue to be a problem as technologies advance and the number of applications increase. That is the reason there is a global effort to effectively better design the protection of IC devices. It's a losing battle. but it's a continuous battle. It's never. One vice president asked me one time at TI, you working in this field for more than 25 years and you haven't solved it yet. Yes, nobody can solve the problem. You can only, it's like the firefighting, you continuously fight it to contain it. That's the idea, okay? So let me show you from ESD to lightning all the different pulses that can happen. So ESD is classified anywhere from 1 volt to 15,000 volts. In that range is called ESD. It's a very short duration pulse, less than a microsecond. It is less than 10 nanosecond in rise time, so that's a very short pulse and it's very low power. So that is what ESD is. Whereas electrical overstress is a low voltage, few tenths of volts only. It's not thousands of volts because you're just misapplying some voltages. It's much greater than a microsecond and it has a very slow rise time. It is low power also. But in contrast, lightning is extremely high voltage and extremely high power. So we can't protect against lightning on an IC chip, but we can protect for ESD and an IC chip. So IC devices used in, as I said, automobile, medical, military, consumer, all of them need this ESD protection. ESD protections comes from static control and design of ICs. There are two ways to do it. One is how to stop from high static fields being in the production areas, so you control that, and I will mention that to you. And then, of course, the IC protection. ESD protection requires, EOS protection requires careful applications. Now, in contrast, for lightning, we have houses, buildings, planes, electronics need lightning protection. As you know, most of you know of lightning rods and surge protection. So that is the distinction. So we focus on ESD in this seminar. So the question now is, how is ESD encountered? Humans with surroundings from body capacitance, typical human body capacitance is about 100 picofarads, but this depends on body mass, temperature, and humidity. Of course, someone who is very big has a higher capacitance than people who are smaller people. Fortunately, most of the assembly is done in Asia where people are smaller than being larger. And if you drink a lot of beer, your capacitance will be more than 100 puff. So you cause more damage to devices. So we had to take some average capacitance. So everybody said, okay, 100 puff is a good average number for the human body. So when these humans interact with devices like cell phones, touch screens, their body capacitance is sensed, causing ESD events. Okay? So charge can be stored or accumulated across physical bodies when isolated from ground. It's not only just human bodies, but also packages that are in an assembly area can acquire charge and potential themselves. So when you are about to touch an IC device, notice that blue spark there. That is the static discharge from your fingertip onto the IC pin. And that, while that energy is very small in microjoules, it is enough to damage a transistor damage. As you can see, the damage is from drain to source of a MOSFET that has blown across. So this is, this is a certain level of that potential from the human body can destroy a pin. So continuing on how ESD is encountered, it can be human body, a machine, or an electronic equipment, or example IC itself. When the IC is in a handler, in an automatic handler, it could have a potential, and when it slides and hits the ground plane, or when it's put in a socket, or it's in machine handling of the devices, any one of those, when it touches a ground plane, you get a discharge. Just like human, a charge touching a pin can cause discharge, or a IC itself can get discharged when it is hits the ground plane. So ESD then is the transfer of electrostatic charge between bodies or surfaces at different electrostatic potentials. It is the differences in the potentials that causes the discharge. So you notice that an IC sliding down and touching a grounded plane causes a zap right there. And that is the damage that is seen in a gate oxide of a MOSFET when that happens. So these are the two events that are of main concern for the IC devices. These are only for the assembly area. And then we will talk more about a system where it is the IC is outside the assembly. So how do we test then? How do we know that this device can survive the threat? So what is once is called the human body model is the human body capacitance and resistance is involved in the model. So what you have is an equivalent circuit is you charge a human body potential like 2000 volts to that 100 puff capacitor, which is the capacitance of the human body, and discharge through 1.5 kilo ohms of resistance. Now that 1.5 kilo ohm is your finger resistance. We are all thankful that we have a resistance. If we don't, we would be killed, because with that 2000 volts, if it is with a small resistance, will give you a lot of current. But because of that finger resistance, we have only, the current is limited, even if it is a few thousand volts. And so you put the device in a socket, and then you charge the capacitor, and you discharge the capacitor. So then you generate a pulse that is shown in the bottom, which is given by this. 1.3 amps. 1.3 amps is because 2000 volts divided by 1500 ohms is 1.3 amps. So that's the peak current. And the time constant is 100 puff times 1500 ohms is 150 nanoseconds. So one time constant is 150 nanoseconds. So human body event is a decaying waveform. It takes about 3 time constants before all the current disappears. So it's energy under that curve is what causes the damage to the IC transistor. So this is what is the human body model that is shown here. Notice the rise time is pretty fast, but the decay time is long. So once we know this pulse, we protect any kind of circuit that we want to protect that can face this threat and be able to not damage up any of the transistors. So how do you test for the package charge itself? We talked about the human body model. The other one is the charged device model. The device itself is charged. Then the way you test that is to have a charging potential, and then you place the device. I have to induce a charge on the device. So what I do is I induce a field so that if I can now charge the whole package up to 500 volts, for example. If it is at 500 volts, so every pin here is at 500 volts. Now if I put a ground probe on one pin, it discharges, the package capacitance discharges from that pin. So I charge again and check the next pin, charge again and test the next pin, and so on. So you want to make sure that every pin that can ever be able to touch a ground plane is able to handle this pulse. But notice this pulse is very different from the previous one. It is much higher current, but very short time. It's only less than a nanosecond, and it's a much sharper rise time, 200 to 300 picoseconds. Although this energy is under this curve is lower, but what happens is when you have such a sharp current rise in a very fast time, any IR drop in any metal connection, let's say there are something like 1 ohm or 2 ohms of resistance, at 10 amps, at 2 ohms is 20 volts instantaneously. That's the reason it blows up a gate oxide like what you saw. So in the previous human body model, it was thermal damage. In this charge device model, it's the oxide damage. It's because a sudden voltage appearing across a gate oxide of a MOSFET transistor. So you remember seeing that picture in the pinhole in the oxide? That's because of this. So these are the two distinct models that people design to make sure that they can protect on these chips. Okay, so what happens now when all these ICs are placed inside a circuit board? Now, let's say you protected all of them, but now they are reaching external buses. So these ICs are not in a production area anymore. They are in the outside environment. Where is the outside environment? Like your USB connection, HDMI connection, your camera connection. All of these are now external pins. Now, in the external events, there is no control of ESD. Remember, in a production area, you control ESD, so there's only a few thousand volts. But in an external world, it is now, it's a free for all. It can be 15,000 volts, 30,000 volts. So you have to be able to protect whatever that faces the external world. That's a different kind of strategy of trying to protect the external world. And I'll talk about that in a minute. The external world events are represented by a different model, 150 power, 330 ohms. And this represents someone like taking a screwdriver or your car key, touching on the external ports. If you're charged to 15,000 volts, you can produce current as high as 30 amps of current. Notice it's a very weird looking waveform. So all these pins that are in the external world must be able to handle energy like this. So to sum it up then, all the internal pins are protected for the two models that I already talked about. All the external pins require a separate type of protection to protect. Then you have the total protection for a system. Once a chip is inside a system, it doesn't face any more human body threats because you are now touching only the PC. You're not touching that pin anymore, but you are touching external ports of the electronic equipment. So what is the time domain for each one of them? We talked about human handling. It's about 150 nanosecond. And then for package self-discharging, that's about much shorter time scale, about a nanosecond. And then here is someone fooling around in the back of a computer, touching with a screwdriver, and they are not supposed to be doing this. Do you know why they test for this? Is to simulate the worst thing a human being can do. Okay, that's the reason. It's not like this is going to happen every day, but you always have to design for the worst case scenario. And that's what that is about. And when you do that, you generate pulses that are quite severe in magnitude. Okay? So HBM and cerium represent low energy in microjoules, but external events called IEC, or International Electrotechnical Commission, who have established this waveform, and they represent much harsher events at 8,000 or even 15,000 volts. Okay, so when you rub that your cell phone on your sweater to polish it in winter time, you are really, it's a scary thing to do. Okay, so those are all the events that are so harsh for the electronics devices. So now, if we look at the logarithm of failure, versus the time to failure, you can see different time domains, what does happen. That is, this charge device model that we said was a very fast rise time event, they are in this time domain. First you have the adiabatic, and then you have 1 over square root of t. That means it is proportional to 1 over the square root of t is the logarithm of failure to power reduces by that time scale with the logarithm of t. So that is that, the human body model is this. Now what happens now if you go to a much longer time frame? Now notice that the power becomes constant. So that is the electrical overstress region. So here is your ESD and here is your EOS. So now there is, because there is such a long time power to dissipate, you can get very severe damage. Notice for the ESD, the damage is very tiny amount of localized damage, whereas under electrical overstress is much higher. So what that means is under ESD, heat does not disperse much, causing localized failures like what you see there, but overstress is wide spreading of heat, resulting in large areas of damage. Okay. Now, we talked about these events, but are there other kinds of events that take place other than just these events? Sure, there are other kinds of events. As I said, that we talked about human body, charge device, the external pulses, and electrical overstress. These we talked about. But there are other things. What is called the cable discharge. That is, at the Ethernet connections and other ports, you can, if you drag a cable and connect it, you are now discharging that cable onto the device, especially at Ethernet I/O. So that's one event. Another event is charge board. Now if you have a board of components and you're plugging it into a mainframe, you are now, the whole board is charged, wherever the connecting pins are, now you get an event there. So that's that. And so every stress type needs attention. All internal pins of an IC need protection clamps, as we were going to talk about. All external pins need protection for the external events, and on-chip protection is not applicable to any of these charge board events and electrical overstress. These are separate fields, these are customer handling and so on. So what I want to show is a time scale of all these events. But before I do that, notice one thing, that the x-axis is broken between 100 nanoseconds and a microsecond, and microsecond milliseconds. So this is time is broken there, but you can see what these events are. This is what that human body event looks like. It's about 1 amp of current or so for this longer time. And that package discharging is this event that is taken. So these are the two events that we are protecting with an on-chip protection devices. And then a cable discharge, that's a pretty big long pulse with higher current. And then the external events outside the environment protected areas, this is what happens every day when you're handling any of these your electronic equipment. And then the electrical overstress is much longer. Because the time is so long, it goes into ... here, and that's the reason you get so much more damage on the devices. So ESD events are in the range of 1 nanosecond to a microsecond with very fast rise times, and EOS can be into rise times that are slower. So now the question comes about is, how do the factories protect these devices during all this fabrication, assembly and test and all of that? It is controlled by 3 different ways. One is grounding the person with a wrist strap to ground. So notice that the wrist strap to ground is attached here, and you can see. And then the next one is grounding the work surface. See the work surface. So in every lab, ESD lab, or in the test areas, when ICs are handled, these things are followed all over the world, no matter where it is. If they don't comply to these things, there is no IC protection. So, protection, that's what it is. Now these things that look like bags of cocaine are actually ESD protected packaged devices. Now, the devices are also packaged in some anti-static materials and shipped over. So these are the three ways. If people follow this, usually nothing more than about 1,000 volts is the threat. That's the reason we protect for a couple of thousand volts is all the protection that we do on an IC pin. With these control methods, only a few hundred volts impact will ever occur in areas. Therefore, ICs are designed to meet about for 2,000 volts for that human body and about 500 volts. Packages really don't get charged up to several thousand volts, but at least a few hundred volts. So that is the whole idea of this. So if you look in a nutshell, here is, in a fab environment, here are the vapors that are being produced. Now they're not ICs yet, it's just a vapor. But during vapor production itself, you can have a lot of static fields, especially when you are spinning these vapors or rinsing them with water. And all of these can have a lot of static fields. So what you do is, you use ionizers and static handling procedures to make sure that the vapors are not damaged. I don't go into details. There are other things like the antenna effects that do take place with long metal lines on vapors and so on. And then during the IC assembly and test, there are measures like grounding and ionizers are done there. And then during assembly and repair, and also grounding and ionizers. So those are done here. And then at the end customer, shielding and pre-running of ground. Usually when people look at the back of their laptop, you can see a shield that is there that is to stop you from touching those pins. Okay, it's a grounded shield that is put in there. So this area inside is called ESD protected areas, EPA. So we take care of the devices here. Once they come out, then it's a different strategy of those devices, okay? Inside protected areas, static control methods are used. The same methods are used all over the world. IC device during assembly and handling need on. So although you do that, or a few hundred or 1,000 volts is done here, you still need protection because people are going to handle these devices in production areas. So now we're going to talk about how do you protect those IC pins, because any pin that is external to the package is a pin that needs protection. So what do? Here is a input output. Let's say here is an input pad and here is an output pad, and you have an input buffer and an output buffer, and now you need to put a protection device here. We call these ESD devices. Their sole purpose is whenever there is a zap that occurs, they turn on and take the charge away, okay? So that's their only purpose. They discharge the current and they clamp the voltage so that the voltage is not seen at the oxide and doesn't damage it. That's the input clamp. At the output clamp, the same thing, output pad, the ESD device turns on and takes all the current. Maybe some of the current goes inside too, but whatever it is, that's the idea of putting protection devices to both VSS and to VDD and protect the input and output buffers. These are all the internal circuits that could be there. So ESD clamp devices are designed to protect input buffer gate ESD clamps are also designed to protect the output buffer, drain, especially the drain junctions of these transistors. Protection devices turn on only when ESD occurs. ESD devices must have low impedance to prevent voltage buildup at input, and ESD device must have low impedance to prevent secondary current into output. So the devices must have small capacitance, have low impedance, but must be able to turn on very quickly. Turn on and turn off. That's their own purpose, okay? That's what that whole idea of ESD protection device is. Now there are many kinds of ESD devices. I'm going to very briefly tell you a few of them. Now, if all of you understand about a MOS device, right? It is simply the MOS device is a surface device, is the drain, source and gate, and the current drain to source current is this. An NMOS transistor with any bias on the gate would conduct drain to source current. This is used for circuit design. But the currents under ESD are in the amps of range. They are not a few milliamps of current, right? So what happens is this drive current is not practical for conducting ESD currents which are in the amps of range. So how do you use this MOS device to conduct so much of ESD current? And that, unless of course you make it a very, very large MOS device, but that occupies too much area. So what we want to do is, how do we harness the current of this MOS device to protect for ESD? The way to do that is, let's say you connect the gate to source of that MOSFET. Now it cannot turn on as a MOSFET because you tied the gate and the source. So now, if a MOS device gate is tied to its source and current is applied, the drain junction avalanches and the MOS device actually goes into a bipolar mode. So this MOS device, which I will show you in a minute, it becomes actually a bipolar device. That is, if it is bipolar device, now the current is not going to be in the surface, it's going to be through the bulk, and it can handle much higher current level when it becomes into a bipolar NPN device. Okay? So that's the magic. This turns into that, where the drain becomes the collector, emitter, source of a bipolar device. The question is, how does it turn on into a bipolar device? Okay? The NPN performance of the MOS device depends on various factors such as drain engineering that determines the electric field, and it's a lot of complicated physics that is involved in it, but the idea is, if you understand how this device works, you can use it as a protection device for ESD. So let me explain a little bit of the physics, how that turns on into a MOSFET device. Here is now the drain of the device, here is the source, here is the substrate, and what does happen is, first thing that happens is, when the gate voltage is less than the drain voltage, the channel current flows into the high field region in the drain, where the field is enhanced by the voltage drop from drain to gate. And this, what it does is, then it generates electron-hole pairs. And this is what the impact ionization that is taking place. So these holes will flow into the substrate, which is the p-type. So then you have there is always a substrate resistance. There is an IR drop that comes here, all the electrons are swept away into the drain junction. So the electrons are swept into the drain junctions, holes flow towards the substrate. Holes generate what is called substrate current, causing a potential to be elevated. Now the source potential is not at 0 anymore, but it can go to 0.6, 0.7 volts. So what happens when the substrate potential is 0.7 volts and the source potential is 0? you have a PN junction here, a diode, a forward biasing of this junction. This base to emitter junction gets forward bias. So now that initiates the bipolar conduction of this device. So what does happen is the next step is these events lead to increased flow of electrons towards the drain because of the high electric field that leads into an avalanche process. And then the NPN conduction begins with the base current in the field region leading to electron hole plasma. Then when this plasma is created, now the voltage has to drop to sustain the same current level. So what that happens is this can lead to what is called the required drain voltage for sustaining the high current layer is lower. So the drain voltage after it breaks down, now it snaps back into a lower voltage. That's when the bipolar conduction has taken place. So what that means is that the previous actions are what is called a snapback. I will show you the IV of what a snapback is. That's what that is. So the drain avalanches and then the impact ionization and then the voltage snaps back. Now this is conducting in a bipolar mode. The MOS device is now conducting in a bipolar mode. Remember, the gate is grounded on that device. So, but there is a current now from drain to source, which is actually the collector to emitter current. During snapback, impact ionization current supplies base current for the parasitic bipolar transistor action. So there is the base current that is supplied, and then a positive feedback causes IB to increase until thermal heating. So what happens at the localized spot, the resistance drops, and then more current rushes in and more current rushes in, then eventually it leads into a thermal runaway condition. And when that happens, you have the a power dissipation at that point, eventually melts silicon, and you have that damage you saw. That's what happens, and there is a thermal damage that occurs, and that is called the second breakdown, right? The first breakdown is the safe point. This is when the bipolar begins, and the second breakdown is when the device is already damaged. So if you can know how much current can it handle before it gets damaged, you know now how much ESD current that device can take. Okay, per weight, the wider the device, the more current. But IT2 is a measure of robustness of that transistor in milliamps per micron. If it says the IT2 is 10 milliamps per micron, that means if I have a 100 micron wide transistor, I can handle 1 amp of current. See, now I can do an ESD design on it. I can handle 1 amp of current. If I make it 200, I can handle 2 amps of current. Now I know what to do once I able to characterize that transistor. And that's what that is about. And of course, these are all the other parameters, the trigger point, the holding point, and all of these are what's used in the design of protection circuits. So that means avalanche, breakdown, bipolar conduction, filamentary conduction is already device is damaged. If you are monitoring the leakage on that transistor at a certain drain potential, it would stay in the nanoamps, but suddenly it will go up because now the device is damaged. So when you detect that point, that what you're doing is pulsing and higher current till you see a damage. And when you see that damage, you say, okay, that's all this transistor can handle under an ESD condition. Somebody had a question? Yes? No? Okay. So there is a lot of physics involved here, tunneling, band to band, snapback. What is this negative? You see, this is a negative differential resistance. These are all can be modeled and understood about the bipolar physics of these transistors. So that is a MOSFET that can become into a bipolar device. Now there are other kinds of elements that you can use for protection. For example, simply use a diode. A diode is a P plus region connect anode and N plus in cathode, and the diode usually in forward bias turns on around 1 volt and conducts. Notice a diode can handle 20 to 25 milliamps per each perimeter of the diode. So now you know how big a diode to make, how much current it would take. So that's a diode is one way of protecting. And another thing is a reverse diode. Reverse diode is the P plus is connected to anode, N plus is connected to cathode. Now, it's not a forward bias diode, but it's a reverse bias diode. That means it will break down only at the junction breakdown, which is much higher. This will be about 7 volts. But in a reverse mode, a diode, notice the holding voltage is higher, so the power dissipation is higher, so it can't handle as much current. So that's why it can handle only 1 to 2 milliamps per each micron on perimeter. So diode in a forward bias mode can conduct a lot of ESD. But now I can't put a diode between pad and ground. One diode is going to disrupt all my IC circuitry. You cannot have something that turns on at 1 volt. So, but there are ways of using these diodes to build protection devices. And that is the idea of characterizing these devices. So, gate grounded NMOS, which is what we just talked about, this is what goes into the bipolar mode, and it can handle 5 to 10 milliamps per micron. So any kind of process technology, people would be characterizing all these different devices and say this is how much current they can handle, and based on that, you build your protection circuits. Okay. These MOS device that goes into the bipolar mode also can be represented by in equations. You can build a circuit model for it, and you can do simulations as I show here, and that you can do that too. Now, how do you characterize these transistors in the ESD regime? You need a pulse that is equivalent to the human body model, right? You need the same pulse width. So you're not going to get any kind of decaying waveforms. You cannot generate those. But one thing you can do is, what if you generated a square wave pulse that's only 100 nanoseconds in pulse width? This energy under that pulse is the same thing as a decaying waveform of 150 nanosecond time constant. So the approximately the same. So if I can get something that passes with this kind of pulse, 1 amp passes, that means it's the same 1 amp it can handle under a human body even. So now how much protection will I get if I pass 1 amp? Any idea? If I can pass 1 amp of current, how much protection? Will be 1500 volts. Where did that number 1500 volts come from? That's from the 1.5 kilo ohm of resistance of the human body model. So you know now, if I build a system and I characterize my transistor with these pulse conditions, it passes 2 amps of current, then I say, okay, I can use that device to protect to 2 amps, which is 3000 volts of human body model. That is how the design is done. And this is simply done by a 50 ohm cable, that is a matching 50 ohm cable, and you charge the cable and discharge, and you generate a waveform like this, and you can use that to study the transistors. And you can see such a thing was used, and notice these circles represent the data points on that. So you can actually see the snapback occur, the bipolar conduction turn on, eventually the device fails. At this point, I know this is how much current I can handle. This is how it's measured. Okay? Then you know the trigger point with this kind of equipment is called transmission line pulse, or a TLP. Using that, you can measure this transistor, where does it trigger, the voltage and the current, what is the holding voltage it can go to, and what is the thermal dissipation where these two fails. This BT2 point is, it needs to be lower than the gate oxide breakdown of that transistor, because when the clamp is turning on, it's trying to make sure the oxide breakdown limit is never reached. The same thing, the junction breakdown of an output transistor is never reached. So that's what it is, and you need to pass. IT2 represents the current goal for your protection. So that's how protection devices are turned on. By the way, there is another kind of device, and that is example 4. That is called a semiconductor rectifier, or an SCR, which is a much better than a MOS device, is because it can actually handle much higher current levels than this. That is simply an N plus and a P plus in an N well connected together, and an N plus that is floating at the edge of the well, and another N plus with a gate connected to the cathode is grounded. So all that is when I am applying voltage at this point, what will happen is this N plus is connected to this N plus, this junction breaks down, and you have the bipolar triggering of this device that causes the PNPN device to turn on. That is, it's either a vertical PNP or a lateral NPN. Either of them triggering on causes what is called a latch-up action. That is, two bipolar devices turn on simultaneously. If the loop gain of those two transistors is greater than 1, you have a latch condition. Then the device goes into latching mode and becomes into a PNPN device. And this is actually very good in the sense it can latch into much lower voltage like 1.5 volts, and you notice that it handles 30 to 40 milliamps per micron compared to a MOS device only 10 milliamps per micron. So there are about 100 different varieties of these SCR devices. They're pretty complex, but people keep inventing yet a new device, a better device. The whole idea is to conduct as much ESD current as possible by holding the voltage to the lowest possible voltage. That is the whole idea of this protection. So we talked about that semiconductor rectifier. So I identified them as nodes A, B, C, D. Equivalent circuit, you can see that are the node A, B, C. So Q1 and Q2 are the two transistors that turn on if you trigger the SCR, and when it triggers, PNPN device is formed with Q1 and Q2. When the beta of Q1 times Q2 exceeds 1, it becomes an SCR. And so that is how that device works on. It is triggers just like the MOS device, except it says a much lower holding voltage, and it is a more powerful type of protection device. Okay, now I want to briefly mention about a design window. How does the ESD protection scheme work? That is, you have an IC operating area and an IC breakdown area, and you have a thermal breakdown region up here. So whatever you design has to stay within that window. So this is the oxide breakdown or the junction breakdown, either one, and this is the nominal voltage that you apply. So a clamp like this should stay in here and protect this, and before it reaches its breakdown point. That is called an ESD design window. This is your target current, whatever let's say you're designing for 2 amps, that is 2 amps, and this is your trigger voltage, VT1, it is oxide breakdown voltage under narrow pulse condition. It's not a DC breakdown. Remember, under ESD, the breakdown voltages are actually a little bit different because it's such a short duration. If an oxide breaks down at 10 volts during DC, it will break down only about 15 to 20 volts under ESD conditions. Okay? So that's what that is about. That is the design window. So how do you then move this current away with what these kind of protection devices? Here is an I/O pad, here is a diode to VDD, and here is a MOS device that connected to ground. And here is your buffer device here, and what you are doing is you want to protect I/O to VSS, a grounded gate MOS device that turns on as an NPN device, and then when I/O is stressed, let's say you have a zap on the I/O pin with respect to ground, then all the ESD current then flows from this to here. And when similar protection device is placed between VDD and VSS, and that is VDD to VSS is a protection device similar to the other one, and a diode is placed from I/O to VDD, because when you stress from I/O to VDD, the current has to go this way. So that is how the devices are built to protect. I mean, I'm trying to give you the most simplistic pictures. There are a little more complicated things that go on than this. But that's one way of doing it. But the problem of doing this way of protecting is this introduces capacitance and leakage. So I don't want, for when I'm doing high-speed applications, I don't want that capacitance so high. This could be something like 1 puff of capacitance, and I can't handle so much capacitance. I want to be able to reduce it. So then people look for innovative ways to reduce the capacitance. And another way of doing this is, why do I need a protection device here at all? Why don't I build something that I will dump all the current into the VDD bus? And that's another way of doing it. That is called a rail clamp approach. So that means you don't have a local clamp, but all you do is you're putting a blocking diode here. So the current cannot go from here to there, but it has to go only that way. How do I get the current from VDD to VSS? Notice there are 3 inverters with an RC and a large MOS device. Now this is not a bipolar device now. This is a large MOS device to be able to take all that current away. Then all this capacitance is not seen here. And what this does is, when the moment you zap an I/O pin to ground, what happens is this potential is seen right there with a diode drop at VDD. So that means here originally this is low, high, low, high. That means the gate is on. So now instantly this device is turned on and current goes. Eventually the RC time constant is adjusted, so this node is within a microsecond is pulled up to this point. When this is high now, high, low, that means transistor shut off. So that MOS device will stay on for a microsecond, take all the ESD current away, and shut off. So now you see all the protection is put on the VDD pin. Now you have different IOs there can all share the same protection device. So this is a better way of doing protection. Okay, so that is what that is all about. Now what happens if you have different power domains? Power domain 1, power domain 2, then you have to have paths in between. So if I stress one pin with respect to another pin, the current has to flow this way. So I make sure all my current paths are provided and the whole chip is protected this way. Now I want to briefly talk about a system. Now we only talked about the IC pins, but what about a system? So here is a computer or whatever that is, ESD field coupling through external vent holes. You can have all of these many different effects that take place. Here is someone touching with a screwdriver in the back of the computer. Here is someone bumping their chair into the computer table. You generate electromagnetic fields here. So you have to make sure all of these electronics are protected for all these events. So electric magnetic fields produced by ESD coupled to the system in multiple ways causing failures. Remember, the IEC method is used to represent a charged human holding a metal discharge, metal object to discharge. That's the worst case stress that you do, and you make sure all your interface pins like HDMI, USB, all these pins can interact with that. So how do you protect them? When an IC pin, all the internal pins you already took care of, but the external pins you have to put a Zener. Big Zener devices, so that you can, on the printed circuit board, these are put in here. Common strategies with PCB protection, these Zeners are put in there. Some people try to put a huge protection device on the chip, which is, do you know why they do that? Why they don't put external and they want to put it internal? These things cost about 50 cents each, and the customer complains saying 50 cents is too much because I have to build millions of systems and I don't want to spend money. You put the protection on the chip. But the problem of doing something like that is, now remember, these are handling those 15 amps of current, 30 amps of current, and you can't build a big device on a chip. When you do that, lot of fields are generated and you can disrupt the IC function and all of that. That's the reason people recommend try to terminate it outside the system right here, so that only some energy goes in and you deal with whatever energy that goes in. So the way to do that is, if you put an IC on chip, then there is a lot of return paths, and you're trying to terminate such high energy into this thing, which is not a good thing. But what you do is you try to put it externally, so everything is terminated, only small amount of current goes into the chip. And once you do that, you are doing a much more efficient. This is where the industry is now. Everyone is trying to figure out how to do this more efficiently, so that you know exactly how much current is going in. So how do you know how much current is going in? Here is the IEC external terminals, and here is your IC pin, like a USB pin that's interacting. You need to understand how much current is actually going in from there to there. All those Zener clamps, it's not going to, even at those currents of 30 amps of current, the Zener voltage builds up, although it triggers at 5 or 7 volts, it goes up to 30, 40 volts. If it is at 40 volts, depending on the source impedance at this point, you can get still a significant amount of current going in. So how do you mitigate it? You mitigate it by putting inductors, capacitors, filters, all kinds of things, and all these filters, they have to be able to handle the USB high frequency. So this is a very complex thing of protecting now the whole chip. So your Bluetooth, phones, all of these that interact with the external world have internally a lot of protection elements that protect it from these external events, as well as some external protection device. So those are the different things that we do. So since this is meant to be a basic protection introduction lecture, I will summarize here. For those that are interested later, there is more advanced approach to this, that is now what is the advanced protection, how do you handle protection with such low capacitance so that you can have 35, 40 gigabits per second that signals can go in and still offer ESD protection, and also what's happening with gallium arsenide, nanotubes, IoT devices, and all of those. So right here, let me summarize here. ESD events are fast with short rise time and short durations. ESD voltages are much higher than IC operating voltages. ESD currents are much higher than IC design currents. So the current regimes are very different. Mostly the involved ESD event energies are low, but can damage IO transistors if they are not protected with clamp designs. all pins of an IC package need protection. Protection designs involve understanding of the high current behavior and to safely discharge high currents. The basic lecture will cover all the essentials of ESD. There is an advanced lecture that will talk about lot about RFIOs and 3D ICs and all of those other things is involved here. But right now, this is the fundamental understanding about ESD and protecting the electronics world. So I will stop here and let me know if you have any questions. Thank you.
I had one of your very earliest slides when you were talking about the failures. You had 35%, about 35%, and you said, and that's...
The number changed, did not change in the last 3 decades.
But yeah, I guess what I don't understand, I'm sure that's not the failure like before you ship to the customer. Is the actual IC yields like 99 or something?
Yeah, those are many involved with the customer returns.
So that, okay, and how far does that go back? I've got a 6-year-old laptop, and I think it has some of these problems, but you know, just like in the first
I think
year,
your 6-year-old laptop is more with the hot carriers and slowing down of the transistors.
It wasn't hit by lightning.
Oh, I think that's just as good as anything else, with however good the shield is.
But when you say the failures, that's returned within the first year?
From IC chips that are returned from the customers.
The
The customer says the system failed, this is the chip that failed, I want you to find out why this chip has failed in my system.
That's like within weeks or months of them buying the chip.
Right.
Okay.
Yeah, right.
I didn't know what that meant.
Yeah, but I do want to tell you, you really don't know what those customers are doing. They are mishandling. I can show you the fishbone diagram. It is scary. There are something like 300 different events, surge events, e-field events. A lot of things can cause all these failures. The switching of capacitors in systems. There are too many things to talk about. But this, I do want to tell you though, the last 3-4 years, the industry has spent a lot of time figuring out where all these failures are coming. Now in the automotive industry, they have this big fishbone. Every time they see a failure, you point to which bone of the fish is this and how do we prevent it. There are many different ways. The ECU connection in an automotive, where one ECU1 and ECU2, one is charged and the other is not charged, you're connecting the cable. You can have damage on the IC, but it's not the fault of the IC, it's the fault of the operator. So that's where that is. All I want to say here is that if you have the fundamental ESD protection, you shouldn't get any failures. That is for the yield loss. And by the way, I didn't talk about what people do in their garage, okay, when they buy a DRAM or SRAM or whatever microprocessor. We don't, because we really don't care what they're doing. We can't protect how people handle in the outside world. We can only protect what is done in an assembly area. It is important because there are 40 to 50 different assembly areas all over the world, and all of them must comply to those requirements to control static fields.
No. Oh yeah, a question.
So I talk about the speed values of the ESD. So what's the maximum frequency say conventional ESD can support?
I couldn't quite.
Yeah, you're asking about the maximum. Are you asking if this ESD protection
Very high speed, high frequency. What's the maximum frequency of ESD can support?
Oh, yeah, is there some limitation? Does the ESD protection limit the high speed frequency of your chip?
Yes.
Yeah, I skipped a lot of slides, but let me just show you uh, your question. Here it is. The loading capacitance and the data rates. So everybody thought that I have to design for 2000 volts protection. What we are saying is if you design only for 2000 volts protection, you will only get 5-10 gigabits per second. So if you really want very high speed operations, you make smaller diodes, lower capacitance, and all of that gives you much higher. So that is where we are right now. We are at the 50-60 gigabits per second. That's where the data rates are. Okay? This is, why do we need such high speed?
I mean, right now, there's many, say, chips operate at near wave, like hundreds of gigahertz, or near hundreds of gigahertz, like the tens of gigahertz, like beyond the R frequency. So conventionally, when we designed the millimeter wave chip, we don't put ESD at the higher port to prevent say bandwidth limitation. But right now, since single bars only support like 40 gigahertz frequency, so it's still far from the millimeter wave band frequency.
Yeah, I'm not sure I understood all the question, but I do want to tell you is that companies like Cisco that are building these high-speed systems, they need high-speed operation is more important than the ESD protection. So now the question is, well, of course ESD protection is needed. What do I do if I now go, I can only protect to 500 volts instead of 2000 volts? The answer is better control in the factory. Okay? So there are, although I showed you a simple thing, they can control a factory to 10 volts. It is more expensive, but that's where the technology is going now. You have to control to lower voltages to get higher speeds. And why do we need higher speeds? It's your fault, because all of you are impatient when you're trying to download any picture. Because everybody demands higher and higher speeds, so the systems are built at higher speed. Nobody is patient enough to wait around, and that is the reason it has become a big challenge, and that's why we are working on what is called ultra high speed ESD protection. There are many, many innovations that are possible here, but that's where it's such a field where a lot of people are involved in designing these challenges. I didn't mention to you about RF. RF is even worse. You cannot, RF is so sensitive to the noise gain, and any of these, so any small diode of ESD can really disrupt the RF performance of these devices. So then what you do is what is called a design space. You work with an RF designer and ESD designer, work together and saying, I put an inductor, I put clamp on this side of it, it will not degrade the RF performance and still give me a minimum protection. 100 or 200 volts protection is all you can do with an RF pin. So there are many other challenges like this. Yeah.
I see DoD funding for purposely taking out electronics in vehicles for like electromagnetic pulses. Is that related to ESD, or is that some other failure?
Some other failure. Yeah. Mm-hmm. Yeah. But for the next few years, it is going to be such serious thing that the ESD Association is trying to approach DoD for some funding to understand about how to, especially now we are getting into more of the 3D ICs, gallium arsenide devices, gallium nitride especially. These devices break down at a couple of hundred volts. That's the only protection they have. Is that and they get easily damaged. You cannot build ESD devices out of these technologies. I have all the slides and all of that. That's more for more of a graduate level class that you talk about. Okay? So that's where the technology is going. Oh, yeah.
Kind of why it will be like more challenging for the ESD protection.
Could you speak up a bit? I think you're having trouble.
Yeah, there's ambient noise here. There's a kind.
You mentioned if we goes to like more advanced technology, like 40 nanometers, 7 nanometers, the ESD protection will be like more challenging. So kind of why it's because of the device size smaller, so it's maybe more vulnerable to the ESD.
Yeah, let me tell you one thing why it is challenging. The microprocessors have thousands of pins now, so it's not a few pins. So the chip size is as big as my palm. The chip is so big. And what happens if the chip size is so big? You get more discharge current under the charge device model. It's for the same voltage of 500 volts, a small device might only discharge 1 to 2 amps, but a big package would discharge 14 or 15 amps of current for the same voltage. So now you are trying to deal with such high current with a microprocessor built with very thin gate oxides which break down under ESD regime something like between 4 to 5 volts. Imagine that. Now you're trying to build something that will clamp to 4 volts. Any kind of little resistance in the bus can actually increase. So diode has to be so small. And now that means you cannot reach the levels that you're trying to reach. So that's the reason there is a whole revised thinking about I should be designing for current, I can't be designing for voltage. It's the current that makes any circuit application limited. How much current can I handle? So, if you like, just let me know and I'll give you more information. You get my email and you can ask me questions on these things. Okay?
I should mention this is being videotaped, so hopefully we'll be able to put that online if you want to review some of this, and that would include your email and contact info.
Yeah, yeah. Fortunately, I don't think you've decided to put an exam on this class, right?
Go please make one up.
We did that at the University of California, Santa Barbara. You should see how attentive to the students were.
Only the students have to take it, not the faculty and staff. Why don't we take one more question, and then I think you're willing to stick around for a while if there's more, but is there another question? Yeah.
I'm just interested in the design flow of the ESD. So it's like if I have circuits that is very sensitive to the impedance for RF circuits, then it has to have some impedance matching that needs to be done. So
Right.
once it's designed and you add ESD protection, what if it's going to affect the matching? And
It's a real challenge. That's why I need to show you the slides about the space that is available to share between ESD and RF performance. So there are a lot of techniques that are involved with putting those inductors into the circuits so that they're transparent to RF but can mitigate some ESD. So there are a lot of circuit techniques, a lot of classes that are offered on RF design for ESD. So that's a completely more evolving type of field that is coming on. So RF is very, very sensitive to ESD. In fact, RF designers don't want an ESD device, nothing. Okay?
I'd suggest we thank the speaker again.
Thank you.
For those of you that have to leave and go ahead and you're willing to stick around, I think we have some room for considerable more time if there's other questions.
Yes, thank you very much for your attention.